Hello, good evening everyone. This is Celso Batalha, Astra 10, and let me just get this window going. You know. And I should be sharing my screen with you now. And today I would like to remind you this coming week. Oh, wait a second, I have to start taping for the conference too. Okay. All right. So again, welcome every. Oops. Okay. Now I think it's serious. Uh, welcome everyone, and this is Celso Batalha, Astro 10, and Evergreen Valley College, and I would like to go over the subject of today's, or in fact this week's class, which is light. And I had Harry. Harry's back. Hey Harry, how are you? I'm just starting taping. And I saw that you streamed from the Griffin Observatory. It was cool too. We had a big crowd in the observatory, but it was all cloudy, and so after the eclipse ended, then we could see a beautiful moon. And I was kind of close to home. We went up to a hill nearby, and yeah, and the moon was pretty much. We could see off and on in eclipse through the clouds as the eclipse progressed, the clouds became a little bit thinner, and then we could see better. And eventually, by 8:20 or so, we could see the moon coming out of an eclipse. That was very gorgeous, and I hope you had a good time. So, my daughter, she works in astronomy too, and she's doing a graduate thesis on the subject of planetology and atmosphere. And in fact, she's involved with the development of techniques that will enable astronomers in 3 or 4 years from now to determine if certain exoplanets have or have not conditions for hosting life. And I asked her to come to this chat room and talk a little bit about, oh, and she's there, and talk a little bit about what was in the news today about Mars. Hey Tasha, can you have your microphone in? I, 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 oh, now I can hear you. Yes. So, okay, I will let you speak most of the time because when two people speak, I think it doesn't go through. You can start out video if you want, or you can just talk. So pretty much, the floor is yours. I think you could. Let me see if I can open. I should pause sharing. And so there is a page. I'm opening a white page, like a blackboard. Try to see if you can have the buttons working, so that you can have your computer displaying things on the whiteboard. So this is pretty much during Martian summertime. Can I'm not seeing your images. Can you put in the whiteboard? Oh, okay. So you guys didn't see the water streaming down. You found indirect evidence that water was there. The whiteboard is white. No, I can't see anything. Oh, now I can. It's pretty much gullies. Look like gullies. Natasha, Tasha. Harry is asking if these streaks, these gullies, go away during summertime. During the summertime. Okay. 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 I see. I see. Yeah, that's what Harry was mentioning here. Uh, right, right. So based on the size, I mean, these guys are. You said 4 meters wide and 100 meters long. So based on that size, if water is flowing, how many minutes or seconds or how many hours would you expect to? I mean, would you have to have your camera there in order to see the water flowing? I mean, how long did it take the water to flow to create these gullies? Yeah. Oh, so they don't erode away with some dust storm or I mean they preserve from year to years. So okay, Yeah, I see. Wow. Okay. 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 Salty. So I have a yeah. Salty water. Okay, well, a question having to do with this week's class. How do you know? How do you know they are salty? I mean, how? I mean, you guys did you guys collect any sample? What's going on? Okay. Signature. Signature. Yeah. So every single molecule, depending on the temperature and the type of environment it has, if there is some lights going through, it's gonna imprint some signature on the light. So you don't need to get material, collect material to know what is in there. Okay, very good. But does Mars have enough water vapor or some sort of a humidity in the atmosphere for those minerals to to suck it in? Okay. Okay. So that's why in dry food that we buy to go hiking, there is a little bag with minerals in it. So they suck it, the humidity somehow. Is that kind of the same idea? They are pretty crunchy, by the way. I see. Yeah. Okay. Very good. Very good. Excellent. Very good. It's always good to have somebody that's working with this stuff to tell us what's going on. Well, but it's interesting for what we are learning now. Harry, do you have any question? Harry, do you have any question for her? Tasha, can you read the question? Are you guys talking about water ice or carbon dioxide ice? What type of ice is this? Water ice. Is that correct? So that has to be water ice. Okay. 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 Now, what is the connection of this with life? I mean, are you guys expecting to find some sort of a still crawling and alive biological activity, or are you trying to find some fossils or what? Okay. Okay. All right. All right. Okay, Tasha. Very good. Excellent. Thank you. Yeah. Thanks a lot. All right. Bye. Take it easy. Bye. Talk to you later. That was cool, huh? That was really cool. Okay, so let me go through our. Let me see things that I would like to remind the class about it. It's right here. So this week we are on light and telescopes, and but next week exam one. So exam one, how it's gonna happen? I will have the exam open Wednesday at midnight, and the class has the entire day to, on Thursday to complete it, but it has to be completed in 1 hour. And once you open the exam, you cannot close, you cannot, go take a coffee and go dance salsa and then come back and answer the phone. So it's 1 hour. You open the exam, you have 1 hour to complete it. And once you complete, if you don't complete, Moodle is going to give you whatever grade you have up to that moment. Now, I know situations happen. Sometimes the computer crash, or and then when you try to come back again to the exam, it doesn't allow you to come through. So all of these issues happen, and what I do, I allow a second attempt on Saturday. So, but the second attempt exam you see is not the same. So we might have some identical questions, but it's not going to be the same. So I recommend that you try your best to get exam done on Thursday, and then you can try again on Saturday, and I will collect the highest score of both exams. Yes, a multiple choice. You don't need the Scantron, and you can do in Moodle basically. So just make sure you find the proper time to have it completed. DSP students, just send me a reminder note that you need double time, then I can prepare a specific exam for those students. And I'm talking general to the entire class. So exam is lasts for 1 hour, depending on documentation that I have received in the beginning of semester. Some students have extra time, and I can provide that, but I need to be reminded about it so I can make plans for it. And the chapters is 1 to 4 exactly, don't include formation of planets, that's next week's subject. And that is our first exam. I would like now, I still have some good time, and I would like to go over this chapter. And for some of you, oh, you are not seeing my window now, just a second. You're not seeing my window. Oh, no audio? Oh, what is no audio? Can you hear me? What do you mean by no audio? Oh, okay, okay, very good. All right, so let me see here, so I can show the window. Oh, you can you see my window? No. Can you share? Okay, got it. Okay. So can you see this light and telescope right here? No? On the whiteboard? Okay, let me see. Okay, I think now you can see, right? Should be fine now. Okay. Let's see how that goes. Yeah, so telescopes. So basically, telescopes. Well, why telescope and why this chapter is considered kind of the fundamental chapter in our course? It's because if you think about science, and this is a science-based course, if you think about science, all the achievements of science are based on first you observe nature. That's the first thing. You observe nature, and then you determine there are some regularities going on in what you observe. So there are some features that repeat itself, and then you suspect there is some underlying law governing that process, and then your job is to try to find what those laws are, if there was one or more, and then you have to create some hypothesis how all of that happened. So, for instance, laws of gravity. So Newton thought that gravity was the result of a natural attraction that exists among bodies that have mass. And so the strength of that force depends on the product of the mass divided by the square of the distance between those objects, and there is a constant there multiplying those the multiplications of masses. So and then you go to your laboratory, and then you can you can test this hypothesis. You can create a little model, miniature of your landscape or miniature of the stage where your observation is taking place. So you do that in a laboratory. Okay. So, but eventually you have to go to nature and really collect data, and you have to put your senses on it. You have to see, you have to smell, you have to touch, you have to quantify. So you have to have nature under control. How can you do that in nature, in astronomy? How can you collect pieces of quasars and bring to the laboratory and analyze quasars or analyze galaxies? Quasars, for instance, we are going to study this in the future. Quasars are very energetic objects. Chances are, at this moment in the universe, they don't exist anymore. They have evolved to something more modest, and not so full of energy as quasars used to be in the past. So why do we observe quasars? Because they are so far away that only now the light of these objects arrive here in our telescopes. So how can we talk about things that exist in the past and we don't have the evidence right now to support? So this is why, and because of these questions, this chapter is so important. I mean, although we do not collect pieces of stars, we do not collect samples of galaxies and bring to the laboratory, we can observe them. So observation is the keystone of astronomy. So you collect light, and as Natasha indicated in this in the interview, in the presentation she made for us, you observe things, you collect light that things are emitting to the entire universe. So you collect that light, and then you take that light to the laboratory, in fact to your computer. You use the telescope like a bucket to collect the light, and then take that light to your computer, and then in the freshness, in the relaxing moments in your laboratory or in your office, you just study the light. So light carry properties, and when light interact with matter, and matter consists of particles with mass, with charge, with rotation, with energy. So when these interactions take place, light carry information of the material it interact, and by doing so it can bring that information to astronomers, and astronomers can say, hey, oh, I know what's going on. So that that material, those gullies, they indicate a very salty component, and the type of minerals that are detected in that gullies using the technique of spectroscopy are unique, because I can only detect that if there is water, if those minerals are present, and then I can see those fingerprints. So the universe is full of molecules, full of atoms, and they have their own fingerprints. So when light interacts with the material, it kind of gets most of the properties of that environment, and with it take that to astronomers. Astronomers then require powerful telescopes, and the bigger the aperture the telescope have, better chances of collecting more light, more information is collected, and then we can spend time analyzing. So this is the key aspect of this chapter: spectroscopy and photometry. So let me go towards the end. In fact, all of these you guys must read it and try to get a sense of it. If it's not clear, I can talk to you, but these PowerPoints are very very clear. There are some information you have to memorize, like wavelength and frequency. Wavelength, for instance, light of longer wavelength, if you think about this distance here, it's called wavelength, the distance between parts of a wave that have similar property, like the peaks or the trough points, so this distance is the same. It's called a wavelength, and is usually quantified or by a Greek letter lambda, kind of like this, lambda, lambda. Now the wavelength relates itself to frequency by a simple relation, like if you take the speed of light and you divide it by the frequency of that particular wave, you can determine the wavelength of it. So you can see the wavelength and frequencies, they are inversely proportional. So if the frequency is too short frequency, so you are talking about a long wavelength, right? Because this number is small, this is going to be too big. Does that make sense? So high frequency, if you have a high frequency type of wave, so which means if this number is very high, is a large number, then your wavelength is going to be short. Okay. So this type of thing, you have to kind of make sense of it. The speed of light is the same no matter which frequency you're talking about. For instance, here we have the red, kind of a yellow, orange, green, and violet. So as you go from longer wavelength to a smaller wavelength, so we are probing parts of white light that are of low frequency. So this is low frequency, longer wavelength. And this part of the spectra is of high frequency, and shorter wavelength. But no matter if you are talking about high frequency or low frequency, the speed in which this energy propagates through vacuum is the same. It doesn't change. The speed is the same, but not the frequency or the wavelength. Now, this is somewhat important. Light, the visible light, the one we can see is right here. See that? And this is very small. It's a small portion of what we call the entire range of electromagnetic radiation that includes the so-called gamma rays, very energetic. Gamma rays are very energetic. You can find them in the core of stars because there's very high energy in there, very high temperature. You can find gamma rays in processes related to stellar explosions, supernovae. You do find indications of gamma rays being responsible for or participating in the process. And gas, they're emitting gamma ray type of electromagnetic radiation are extremely hot. Okay. On the other token, if we're talking about the longer wavelength, which pretty much radio waves, so the energy, the frequency is very low. So low frequency, small energy, this wavelength or this electromagnetic radiation carries, or highly energetic, short wavelength, as you can see in this wiggly depiction here, and or rendering here, and longer wavelength, lower frequency. And the visible aspect of it is just a small fraction. And why the visible part of the whole range of electromagnetic radiation is so small? Well, because of the sun. If you stop and think, the sun, our star, is one that has the property, if you give a display of energy or intensity by frequency, by wavelength, the sun has most of its emission in the visible range. Visible. The sun put out some UV, put out some infrared, some radio waves, but primarily the solar energy, the sun's energy, comes primarily in this very small range, which we call the visible light. And because of that, and because we are living in a planet that orbits the sun, we developed sensors that are capable of interact and collect and make the best use of the energy, the light the sun itself produces and escapes through its atmosphere. So it's not by chance we have eyes, they are the way they are. Okay. Now, CCD. So CCD are detectors, linear detector astronomers use nowadays in astronomy. It's very efficient. In fact, your cell phone have a CCD, charge coupled device, and it consists of pixels. They are little capacitors, and these pixels, what it does when light strikes on it, they produce an electric current, and this electric current, this intensity is connected or is related to the frequency in which of radiation that fell on that pixel. So you can take pictures. You can do you can make a rainbow of light object send and imprint that rainbow on a CCD, and then you can analyze it further. And the last thing I would like to talk, it's almost getting in my not 9 o'clock, is about this. Let me see, no, this one right here. Oops. Because spectroscopy is very important, and this is a good application. So remember, in fact, let me go back there. So light is pretty much like this. Let's say there is a gas, a cloud full of atoms in there, right? Like this. And these atoms, they have the property of absorbing a radiation of a specific color or a transition that's very specific, right? So let's say you can produce green, you can produce violet, you can produce yellow, you can produce orange, you can produce red. So I'm just creating here a rainbow, which is so if you take a rainbow with certain proportion of all these colors and mix together, you have the white light. So stars, emit white light basically with different proportions, different intensity of all these different color bands. So, but let's say you have a gas that has a cloud that has a specific gas that likes a lot, and I'm making very simple, that likes a lot to absorb this type of radiation here, the yellow. So when this energy, when this white light passes through the cloud, what comes out is your violet, is your green, orange, and red. But does the yellow go? Well, you know what? My cloud has a Cookie Monster that likes to keeps this yellow in. So the energy associated with this color band gets in this gas and force. I still have to learn how to use this. And force these little elements or molecules to excite themselves, to get more energetic, to collide more, to increase their internal temperature because the energy will stay there. Okay? And as a result, this energy might be scattered and radiated away in all different directions. So what you had originally was a radiation that was coming in this direction and keep going in this direction towards your telescope, right? See your beautiful eyes here, indicating like a telescope thing. So the light goes, but the yellow is gone. The yellow doesn't pass because the gas itself absorbed. So the energy is there now. But the energy doesn't stay there forever. So some of it is radiated away in different directions and is lost. So what this animation show is pretty much like this. So you have a light source like this light bulb, and what you do, you take your telescope and you observe that energy, that white light, through the cloud. And what you see is, well, the cloud is absorbing certain uh, certain range of that energy. So it's absorbing a little bit here in the orange, a little bit here in the green, a little bit here in the blue, and so on and so on and so on. This looks like hydrogen. So it looks like the spectrum of hydrogen. It's a cloud of hydrogen. So if that energy range is just good, that's what you're going to get if you place your telescope here. Now, if you place your telescope here, this is what you got. You got nothing. You got a rainbow, right? Because there is no observer between the source, which is the light bulb, and the telescope. Okay. But if you take now your telescope and you put it right here, right there, see that? Remember in my previous exercise that yellow energy, oops, go back there. This yellow energy is all taken by the cloud, and the cloud radiated away in different directions, and that is what we see. Oops. Wait a second. Now I don't know where I am. Oh, there you go. Did I mess it up? Oh, there you go. So now you're observing that energy, the cloud itself radiate away. So if you put it here, you get absorption line. If you put it there, you have emission lines because the continuum is gone. But if you put it here, you see the rainbow. So again, where does this lacking of energy go? Right here. You can collect them if you integrate and observe in this particular configuration. Okay. So this simulation and animation is very good, and I would like to show it to you so that you guys can try to make sense of it. Okay. Okie dokie. Yeah, excited autumn. Yeah, that's true. Not only people get excited, so you know. Atoms also, molecules get excited. Molecules can be excited by rotating faster or by vibrating faster. So there are two particular ways a molecule can absorb radiation, and a collision too. They can vibrate like a harmonic oscillator, like a harmonic, like the instrument, go open and close at a faster pace with a higher amplitude, or they can rotate faster. So both modes are modes in which energy is pretty much being used by these little systems. Good enough? All right, man. I will. Okay, good night. And I will close the chat room and I will upload the video right after. Good night to you.